So in the previous class, we were talking about Fourier series. And before we get into the topic of Fourier series, I wanted to, what we had discussed was this concept wherein you have an LTI system, you give it an exponential input, the output that you get is Hs multiplied by e raised to st. So this is the Eigen function. And this is the eigenvalue. The same thing happens for the discrete time system. You give it an input z raised to n, and your output is hz multiplied by z raised to n. Okay. The expression for h of s is given by minus infinity to infinity e raised to minus s tau h tau d tau. So h is the impulse response of the system. And h of z is given by summation k equals minus infinity to plus infinity hk z raised to minus k. And although it's not written in the book, these quantities are actually called transfer functions. If you view them as functions of s or z, they are called transfer functions. And we will talk about transfer function of LTI system in probably a month or so from now. Okay, so they are eigenvalues of the LTI system, and they are also called transfer function if you view them as function of s or as function of z. Okay, so this is what we did in the previous class. Okay, let's look at it again somewhat closely. Now let's say I have a1 e raised to s1t plus a2 e raised to s2t. This is the input to the system, LTI system. What do you think the output is going to be? Remember the superposition principle for LTI system. So what do you think would the output going to look like? Someone wants to write in the chat or unmute yourself and speak what the output is going to be.
Would this be a transfer function times the original input?
Okay, it's slightly more than that. Okay, so because
would you have a transfer function for each?
That's right. That's right. And then there has to be an A1. So A1 is the amplification factor for e raised to S1t. So if I look at e raised to S1t, the output is going to be h of S1 e raised to S1t. That gets amplified by A1, which is the coefficient, and then the same thing, A2 h of S2 e raised to S2t. Okay, so once you know what the transfer function is, or once you know this function h of s, no matter what S1, S2, S3 you pick on this side of the system, the output is going to be very easy to compute. So we don't need any convolution, we don't need any particular solution, homogeneous solution. Given the exponential input, we can readily compute the output of the LTI system. Okay, that's the beauty of LTI system. That's this happens only because our system is an LTI system. That's why we can do this decomposition. More generally, if I give an input ak e raised to skt, k goes from minus infinity to plus infinity. The output is going to be summation ak h of sk e raised to skt. Okay, the same thing happens in the discrete time. If my input is summation ak zk raised to n, k goes from minus infinity to plus infinity, my output will be ak h of zk raised to n. Okay, so this property is, so that's why we are studying exponential. We will be exclusively studying exponential signals in LTI systems because of the property that is satisfied by these systems. Okay, the next topic that I want to talk about is Fourier series. Okay, and before I go into the topic of Fourier series, let's do some recap. So we had talked about periodic signals. So xt equal to xt plus capital T for all t in R. So then the signal is periodic. The fundamental period is minimum capital T greater than 0 such that this holds, this xt equals to xt plus capital T holds. The fundamental frequency is given by omega 0 equals 2 pi over capital T. This is all the stuff we had studied in lecture 2 and 3. And then we had talked about periodic complex exponential signal, which is e raised to j omega naught t, e raised to minus j omega naught t. So these are the two periodic complex exponential signals with the fundamental period capital T and the fundamental frequency omega naught. Next thing that we had talked about was harmonically related periodic signals. So these are all the periodic signals with period capital T. These periodic signals must be complex exponential. This would be given by Vk of t, which is e raised to okay, there are multiple ways to write the expression for Vk of t. What is the fundamental period of Vk of t? Can someone compute it and tell me? Or write in the chat box. What's the fundamental period of this Vk of t?
Would it just be K?
It won't be k, it would be t over k.
Okay.
Yeah. Okay, so the fundamental frequency would be k omega naught, and the fundamental period would be t capital T over k. Okay. Now I can construct, because each of these phi of t is periodic signal with period t, I can construct signals of period capital T by just taking a linear combination of phi of t. So I can define x of t to be summation ak phi of t, k goes from minus infinity to plus infinity. And it turns out that because each phi of t is periodic with period capital T, xt is also periodic with period capital T. These AKs are complex numbers. So each of this AK belongs to the space of complex numbers. I just want to place a note here that phi0 of t is actually a constant signal. So a constant signal is, of course, periodic with any period capital T. So there's no problem with having a constant signal in xt. Okay, any questions so far? I hope it is clear why the period of xt is also capital T.
Could you please explain that?
Okay, so let's look at, so we know that phi k of t plus capital T is phi k of t for all t in R. And that's because phi k is a periodic signal with period capital T. So if I look at xt plus capital T, and so I can again write it as k ak of phi kt, which is x of t. So therefore, x of t is periodic with period capital T.
Okay, thank you.
Okay. Any other question? Okay. Let's continue our discussion about x of t, which is summation of ak phi k of t. K goes from minus infinity to plus infinity. So we just figured that phi 0 of t is constant. That's because k is equal to 0. So phi 0 of t is just equal to 1. Now the terms corresponding to k equals to minus 1 and k equals to plus 1 are called first harmonic. Components. So A1, P1T, A minus 1, P minus 1T. These are first harmonic components. These are also called fundamental components. Okay, now if you look at the expression for phi1t and phi minus 1t, this is e raised to e raised to j omega naught t, and e raised to phi minus 1 is e raised to minus j omega naught t. So their fundamental frequency is actually omega naught, and um, so their fundamental frequency is omega naught, and their fundamental period is capital T. And that's why they are called fundamental components, or the first harmonic components of the periodic signal x of t. Okay, that's just the nomenclature. Now A2 P2 of t and A minus 2, P minus 2 of t. These are called second harmonic components of x of t. And you can go on and on. A n, P n t, and A minus n, P minus nt. These are nth harmonic components of x of t. So I give you a periodic signal x, and I ask you what's the first harmonic component of x. You have to compute A1 phi1 of t and A minus 1 phi minus 1 of t. And we'll go over the computational scheme in a bit. And if I ask you what's the nth harmonic component, then you're supposed to answer A n phi n of t and A minus n phi minus n of t. Those are the nth harmonic components of x of t. Okay. So far, we have talked about complex signals. So this is a complex periodic signal. Let's make an assumption that my xt is a real periodic signal. Okay, let's see what happens with that. So let's say my xt summation k ak phi kt is real periodic signal. Then what do we know about xt? Well, we know that xt is equal to x star t. So this star is basically complex conjugate. So because xt is real, implies that xt is equal to its complex conjugate. I'm sure you remember this from your complex numbers class. A real number is equal to its complex conjugate. That's the property of a real number. Let's write down the expression for phi k of t. It's e raised to j k omega naught t. So what's the complex conjugate of phi k?
Isn't it just e to the negative jk omega naught t?
Perfect, yes. So you just have to replace j with minus j, and that will make the complex conjugate of that number. So I just replace j with minus j here, and I get a complex conjugate of phi k. Okay, so now let's look at x star of t, that is summation ak star phi k star of t. K goes from minus infinity to plus infinity. But what do I know about phi k star? Well, we just saw that phi k star of t is minus phi minus k of t. That's the same signal. So I'm going to apply this result to get ak star phi minus k of t. I'm going to relabel the terms. So replacing k with negative k, I get k goes from minus infinity to plus infinity. Ak star changes to a minus k star. Phi minus kt converts to phi kt. And this is equal to ak phi kt. Any questions on this step? This is my xt. So I know that my x star t and my xt, they are equal. And for x star t, I get this expression. And I know that the expression for xt is given by this number. I mean, by this expression. So, and the two expressions are going to be equal because I know that xt is real. So x star t must be equal to xt. And so what do I notice here? So phi k of t is common in both the sides. But I have ak on one side and I have a minus k star on the other side. So this would imply that my ak must be equal to a minus k star. Or alternatively, ak star is equal to a minus k. So whenever you have this condition, ak star equals to a minus k, you will have a real signal, a real periodic signal, x of t.
I have a quick question. How
Yeah.
are you able to, so up above you have phi to the negative, or phi negative kt. How are you able to switch that to?
This equality, are you talking about this?
Yeah.
Okay.
Yeah. Yep.
Right. So I'm just going to relabel k with minus k. So I'm just going to replace k with minus k in this expression. So let's look at it. Okay. So I have summation of ak phi minus kt, ak star phi minus kt. K goes from minus infinity to infinity. Let's define k prime equals to minus k. So what do I get? I get summation. So k k goes from minus infinity to plus infinity. So the k prime will go from plus infinity to minus infinity. But of course, you don't write it going from plus infinity to minus. You just write it as minus infinity to plus infinity. And a k star would become a minus k prime star, and phi minus k would become phi k prime of t, right? But the k prime is basically a dummy variable that we are using for summation. So I'm just representing this k prime with just k in this expression.
Gotcha. That makes sense. Thank you.
Yeah. Okay, so I was writing something here. Let me just write it below. So what we have just seen is xt is real periodic if and only if a k star equals to a minus k. In fact, if you continue the same line of thought, if you continue with this calculation, you can show that if ak is given by capital AK e raised to j theta k, so that's a complex number. So capital AK is the magnitude of AK and theta k is the angle of AK. So if I represent AK by this number, then I can write x of t as a0 plus summation k equals 1 to infinity 2 ak cos k omega naught t plus theta k. So I can just write this as summation of cosine functions. A real periodic signal can be written as summation of cosine signals. Alternatively, if I write ak to be a capital K, no, bk plus jck, then I can write xt as a0 plus 2 So depending on how you represent AK, you can get a slightly different form of xt, but the two forms are equivalent. You can go from this form to this form and vice versa. Any questions so far? Okay, so we started with, let's look at what we have done so far. Right, so we started with harmonically related periodic signals. We realized that all the harmonically related periodic signals have period capital T. So I can take a combination, a linear combination of these harmonically related signals, and what I get xt is also a periodic signal with period capital T, which is actually very good. So now I can construct from harmonically related signals, I can construct periodic signals with period capital T in this fashion. Okay. Then I define what is known as the first harmonic component of xt and second harmonic component of xt and nth harmonic component of xt. This series, so remember this xt plus t is written as summation of ak phi kt. This series is known as Fourier series. Okay, so summation of ak phi k of t, this is known as Fourier series representation of xt. Okay, and we assumed that, so this is the Fourier series for complex periodic signal. We looked at a real periodic signal, so xt is real in this case. And for real periodic signals, you can write the Fourier series in this form where it's the sum of cosines amplified by some factor ak, or sum of cosines and sines amplified by factors bk and minus ck. Okay, with the 2 standing outside the bracket. Right? So this is what is the famous topic of Fourier series. Now let's assume that, okay, so I think let me write down very clearly what we have done so far. So we used harmonically related complex exponential signals to construct periodic signals. Okay, that's what we have done so far. And what we get is xt as summation ak phi k of t. It turns out, after doing a lot of complicated math, any, or rather a large class of periodic signals can be written in Fourier series form. Okay, so I give you a periodic signal xt, assuming that it satisfies certain conditions that we are going to talk about in a few minutes. It will have a Fourier series representation, which means that you can write x of t as summation of ak phi k of t. Okay, so what kind of signals can be written in the Fourier series form? So let me give you a set of conditions called the Dirichlet condition. It's actually a non-obvious result. Okay, so this part is actually pretty obvious. We just, the proof is basically one line proof. You take a harmonically related complex exponential, add it up, amplify it, whatever, you get a periodic signal, no problem. Okay, that proof is fairly straightforward. what I'm writing here in the green font is actually the opposite. So if I give you a periodic signal, you can actually write it in the form of the sum of harmonically related complex exponential signals. That result, this result, is highly non-trivial result. And we are talking about the developments from 1750s to 1850s. Okay, it took us a very long time to be able to establish this result mathematically. Okay, so very, very non-trivial result, and I don't want you to assume that the second statement is actually pretty easy. It's actually very complicated. And therefore, we won't be covering it in this class, but I do want to tell you about Dirichlet conditions, which tells you that if a periodic signal satisfies certain properties, then it can be written in the Fourier series form. So what are those properties? So the condition one is that if you take the integral and the absolute value of x of t and integrate it between 0 to capital T dt, this has to be less than infinity. So it has to be finite. So the second condition in a bounded time interval xt should have bounded variations, which is equivalent to saying it should have, xt should have finite number of maxima and minima. Okay, and we'll talk about some examples that do not satisfy condition 1, 2, or 3. Okay, so the first condition is pretty, I mean, maybe not obvious, but it has to be integrable. It has to be absolutely integrable, which means that if you take the absolute value of xt, integrate it from 0 to t, it should be finite. So the area under the curve of xt should be, or absolute value of xt should be finite. The second is not only should the area be finite, but actually it should have finite number of maxima and minima. So you can't have like an extremely zigzag uh, values of xt, which has infinite number of maxima or minima in a bounded time interval. So those type of signals are discarded. Now, of course, in real world, you don't really see such signals. So it doesn't really create any problem for us because we are looking at engineering systems, not mathematical systems. The third condition is in any finite interval of time, xt should have finite number of discontinuities. Okay, so you can't have a situation where you have infinite number of discontinuities in finite interval of time. Okay, so if these three conditions are satisfied, if your xt, if your periodic signal satisfies condition 1, condition 2, and condition 3, you can write it in a Fourier series form. Okay, you can write it as sum of harmonically related complex exponential signals. Now let's examine each of these conditions. Any questions so far in condition 1, 2, and 3? Okay, so let's look at periodic signals that violate condition 1. Xt and t. So it violates condition 1 because this is the periodicity, and your signal looks like this. It's a periodic signal, right, with period 1, but the area under the curve, area under absolute value of xt, is actually infinity. So therefore, you cannot represent this type of signal in a Fourier series form. This is the area under the curve. And this area under the curve is infinity because this line goes all the way to infinity. So the area is infinity, and therefore this is not a periodic signal. This cannot be represented in a Fourier series form. So such a signal violates condition 1. Let's look at another signal. And this signal looks like something like this. So this is sine 2 pi over t, t between 0 to 1. So it has infinite number of maximum in an interval 0 to capital T, or from capital T to 2 capital T, and so on. So this is also a signal. It doesn't happen in real world. Okay, so this signal is completely irrelevant for real world applications, but for this signal, periodic signal, you cannot compute the Fourier transform. And then the third signal, which has infinite number of discontinuities, the signal actually looks like this. Something like this. So it has infinite number of discontinuities, and therefore you cannot take a Fourier transform for signals like these. Okay, so as you can see, the cases where you cannot take Fourier transform are highly pathological periodic signals. They don't appear in real world, and therefore it doesn't matter if you can take their Fourier series or not. Like, because for practical purposes, we are going to get well-defined signals, which would satisfy all three conditions required for representing a periodic signal in the Fourier series format. Okay, so this is some mathematical stuff, mathematical mumbo jumbo that is needed to make sense of this Fourier series representation. Okay, very non-trivial result, but still very useful for practical purposes. Any question? So what we are
Sorry, I was late to hitting the mic button. My question is for the second graph you drew with the signs,
yes,
or with the sine function, that breaks condition 2?
it breaks condition 2, yeah.
Okay, that's what I want to know. Thank you.
Yeah. It has infinite number of maxima and minima within a finite time interval 0, 1. Right. So this is the learning for 100 years of research by mathematicians. So it's by no means a trivial result. Okay. Now let's say I have a periodic signal xt and satisfies Dirichlet condition. Okay, so the three conditions we just talked about, I have a periodic signal that satisfies Dirichlet's conditions, and it's a periodic signal. So the result is, well, I can write x of t as summation of phi k, ak phi k of t, k equals minus infinity to plus infinity, which is the same as saying ak e raised to j k omega naught t. Omega naught is 2 pi over capital T. Capital T is the fundamental period of x of t. Okay, so some mathematician comes to us and tells us, hey, look, you have a periodic signal. It seems to be satisfying Dirichlet's condition. So you can write it in this format. But as engineers, it's not just helpful to know in what format we can write this periodic signal in. We actually would like to know what the values of AK is going to be, right? So just knowing that, oh, we can write it xt in this form is not really very useful. We have to find the values of AK as well. And then we could do something more useful with the periodic signal. So the question is, how do we find the value of AK? What do you think? Let me write the question. How to compute AK? Okay, so we have 1 minute left. I'm 100% sure that I can't really derive the values of AK within 1 minute. So I'll leave you with this question. And in the next class, we are going to look at how to compute the values of AK for a periodic signal that satisfies Dirichlet condition. Okay, so thank you for your attention. I'll see you all on Friday. I'm going to stop recording
Thanks.
and I'll stick around if you have any questions.